Hello folks, this lesson is going to be on the difference in energy between reactants and products following a chemical reaction. During a chemical reaction, bonds are broken, new bonds are made, and whenever bonds are broken and made, there is energy that is either absorbed, taken in, or released during the process. So as the title says here, we're going to be talking about heats of reaction, heat of combustion, and heat of formation. Different symbols that go along with these calculations, a few of which we see here. So hopefully you remember that this one here, this delta symbol, it does mean a change in. The R in this case is just for reaction during any kind of chemical reaction. And the H is referring to or is for what's called enthalpy. And it's really just the heat. So the change in energy can be in different forms, but most of the time, and the vast majority of it, is in the form of heat, and that's why it is the heat of reaction. If we're specifically talking about a combustion reaction, which we do focus on in Science 30, then it's just a lowercase c here. And in your data booklet, we'll be using a table that shows the standard heats of formation, and that's what the lowercase f is going to be for. So the picture that we're taking a look at here, the flaring that we do see, going up in the gas here, what we would have is the products of a combustion reaction, carbon dioxide in the form of a gas, water also in the form of a gas. What is burning down at the bottom is probably methane, CH4, and because it is a combustion reaction, you also require oxygen, and both of these also happen to be in the form of a gas. So when this does take place, we do have some energy that is being released here. So there's energy released in the form of light, obviously, but also heat. A huge amount of heat that's being released. So because of that, there's actually more energy in the original reactants than what there is in the products. And the law of conservation of energy says that energy cannot be created or destroyed, so that energy can't just disappear, and it is released in the form of heat. So if we do take a look at the energy in the products and the heat that's being released, that will actually add up to the amount of energy what we had in the reactants that we started with in the first place. And that's what we're going to take a look at with some of these calculations. So regardless of whether heat is lost in a reaction, and I'll talk more about this on the next slide, exothermic reactions is what that is when heat is lost or gained, what's called an endothermic reaction. This difference in the energy between the products and reactants, it is the heat of reaction, the change in the heat that has taken place during that reaction. And again, the H, that is the symbol for this word here, enthalpy, which is the heat content of a substance or a group of substances. So I have a simplified version here of the equation that's in your data booklet. So delta H, change in the enthalpy for a chemical reaction. What we take a look at is the sum of the enthalpy in the products. That's what this symbol is, the sum of the enthalpy in the products minus the sum of the enthalpy in the reactants. So yes, it is products minus reactants, even though in a chemical reaction, we of course write the reactants first, reactants going to products. When we do the calculations, it is products minus reactants. So if you end up with a positive answer following your calculations, that means that it's an endothermic reaction and energy was added and there's more in the products than the reactants. If you get a negative answer, that's certainly not wrong. What it means is that energy was released, and that's exactly the example that we saw on the first page with the burning of methane. So the delta H heat of reaction can be measured directly, but we're going to do calculations for this using some of the numbers in your data booklet. So just a little bit more on exothermic and endothermic reactions. Exo, the prefix does mean into, or sorry, out of for exo, and thermic It does mean heat. So in other words, energy is going to be released following that reaction. So if we take a look at this general reaction that I have here, the reactants that we're starting with, they have higher energy than the products that we end up with. How is that possible? Due to the conservation of energy. You can't lose energy, so some energy must have been released along the way. And again, that is going to be in the form of heat. So if we say we have this energy, we'll just call it A. Energy in the heat that's released, B. Energy in the products, C. Then B and C together have to add up to the amount of energy that we started with in the first place. So the opposite is an endothermic reaction. So here endo does mean into, and again thermic, heat. Heat is going to be added, energy is going to be added to this reaction. So now we end up with more energy on the product side than what we started with on the reactant side. And energy was absorbed or added as this reaction was taking place. So heat of formation values, again, this is what is in your data booklet, a bunch of numbers that you do have for the heat of formation of various different substances. And this represents the change in energy when that compound is formed. Most of these, as you will see, are negative, and that just means that when these bonds are formed, energy is released in the process, so they themselves are exothermic reactions. So this is the equation that is directly from your data booklet, more or less the same as what I showed you previously, except we also have this in here. Lowercase n is for moles. So this is why we need to go back to balancing reactions, rating and balancing chemical reactions, because those coefficients represent the number of moles that are used and formed for different compounds in the chemical reaction, and we need those coefficients for our calculations. So for combustion reactions, well, now we just call it the heat of combustion, and again, that is really what we do focus on for the Science 30. So I'm just going to exit out of here temporarily and go into your data booklet. Scroll down to page 5 in your data booklet, and right at the top, what it does have are these standard heats of formation. So this is not, of course, for all compounds. These are for selected compounds that they have listed here. They give the name, they give the formula along with the state, and the energy released when it is formed. So this is the change in energy, the heat of formation measured in kilojoules per mole. So for ammonia, NH4, that is the compound that is being formed from the elements nitrogen and hydrogen. And when it is formed, we get a negative number, negative 45.9. And all that means is that when these bonds were formed in the ammonia, some heat was released in the process, so you end up with less energy in the product than what you had in the reactants that you started with in the first place. So again, an exothermic reaction, and as previously mentioned, most of the numbers in here are going to be negative. I'm going to take a look at a couple of calculations, and the calculations that I'm going to be doing will be combustion reactions. And just so I don't need to keep coming back to your data booklet, we'll be taking a look at this one here, octane. You don't need to remember what it is. It's given to you in your data booklet, as is the heat of formation. And propane is the other one that I'll take a look at. Again, it's given to you here, and the heat of formation. Just a note about the last two at the bottom, they are both water. So pay particular attention to this in the question. Is water in the liquid state or a gas state? So if it is a combustion reaction, we do assume that it's going to be a gas that is produced. So then you would use the number right at the bottom for your calculations, negative 241.8 kilojoules per mole. Of course, if you use the wrong one, then you do end up getting the wrong answer in the end. Elements are not anywhere in the table. So that is really significant for combustion reactions. Oxygen you will not find in this table, but it doesn't matter for our calculations because the heat of formation is 0 for that. And again, it does tell us down here, exothermic reactions, you will get a negative sign. Endothermic, you will get a positive sign. The equation is the one right at the bottom here for the heat of reaction, exactly the same as what I did just show you. And again, they tell you what all the symbols are that we have here. So here we have the sum of. You don't need to remember that. The lowercase n is the amount of moles that you do have. All of that given to you right in your data booklet. So let's go ahead and take a look at a couple of calculations here. So this first one is for the propane that I mentioned. So first thing that you need to do is you need to write the chemical reaction and you need to balance the chemical reaction. In your data booklet, again, it does have different reaction types, and it does tell you that for combustion reactions, what you have is a fuel, and that fuel is burning, and for it to burn, you need oxygen. So that's going to be one of the reactants, oxygen gas, and the products are going to be carbon dioxide and water. It doesn't matter if you write the carbon dioxide first, as I have here, or if you write the water first. It's exactly the same, but it does matter that water is a gas. Okay, so you do need to know that. So the only thing that's going to differ is the fuel. So in this case, the fuel is propane. And again, that's in your data booklet, and it is C3H8. So this is our chemical reaction, but you also need to balance it. Remember that for balancing, what we do is we stick numbers in front, and those are called the coefficients. You can never change the numbers in the compound formula. So propane is C3H8. You can't just decide you're going to change this 3 to a 4, because then that compound doesn't exist. So you can never change those numbers, but you need to ensure that what you have on either side of the reaction arrow is exactly the same number of elements. So on the left-hand side, we have carbon, hydrogen, and oxygen. On the right-hand side, well, you better also have carbon, hydrogen, and oxygen, or it's not a chemical reaction and something is wrong. So we need to balance it, because if we take a look, we can see that there are 3 carbon on the left-hand side, but there's only 1 on the right-hand side, so we need to fix that before we can go on and do our calculations. So for the balancing rules for combustion reaction, oxygen, leave until last. Otherwise, it can create some problems. Hydrogen, until second last. We'll pretend that that says until. Leave until second last, and that means we're with the carbon, and we're going to do this one first. Okay, so yeah, carbon, we have 3 already right here. So this 3, again, after the carbon, that is how many we have. The 8 after the hydrogen, that's how many we have. The 2 after the oxygen, that is how many we have right now. On the right-hand side, this is a 1 here. We don't write the 1, but it is only 1 carbon that we have. So we need to get 3. We can't change that 1 to a 3, but we can put a 3 in front. That 3 now applies to all of the elements after it in that compound. So now we have 3 carbon, and we just balance the carbon. Let's go on to the hydrogen. We have 8 hydrogen on the left. We need 8 on the right. How many do we have now? We only have 2. So what number times 2 is going to give us 8? So we get the same as on the left-hand side. Well, that, of course, is 4, and that's your coefficient that you put in front. 4 times 2. We now have 8 carbon on the right-hand side. So the oxygen, remember that this coefficient applies not only to the carbon, but to the oxygen as well. So contained within the carbon dioxide, we now have 3 times 2, 6 oxygen in the carbon dioxide. And again, after this oxygen, there is a 1. So it is 4 times 1, or 4 oxygen contained within the water. In other words, we have a total of 6 plus 4 equals 10 oxygen on the right-hand side. We need 10 on the left-hand side. So if I put a 5 in front of the O2, 5 times 2 equals 10, and now I have the same number. Always go back and check. 3 carbon on the left, 3 carbon on the right, 8 hydrogen on the left, 4 times 2, 8 hydrogen on the right, 5 times 2, 10 oxygen on the left. Here we have 3 times 2, 6. Here we have another 4, 10, so we have a balanced chemical reaction with these coefficients. So you should be in the habit of using GRASP for all of your calculations. So the given information is really the information in your data booklet. So you are given the heats of formation for all of the different compounds that we need. So for the propane, C3H8, that one directly from the data booklet is negative 103.8. Don't forget the units, kilojoules per mole. For the oxygen, this one again is 0. It's not in your table, but it is at the bottom where it says elements are going to be 0. Carbon dioxide is negative 393.5 kilojoules per mole. And finally, our water, and this one is gas, and that is negative 241.8 kilojoules per mole. So we're trying to calculate the heat of combustion. So the equation that we then have, heat of combustion for our propane, and that's going to equal to, I'll just simplify it a little bit here, the sum of the enthalpy, and this is for the products, minus the sum of the enthalpy of formation for the reactants. Okay, again, products minus reactants. Products minus reactants, not the other way around. So let's go ahead and plug this in. I'm just going to shift over to the left a little bit so I do have enough space here. So this is where we need the coefficients, because also in here, there's the lowercase n. There's the lowercase n. So we do need the number of moles. So up here for the propane, we didn't put a number in front, but it is a 1. Okay, it's not a 0. If it was a 0, then the propane wouldn't be there as a reactant. So it is 1 that we do have. So we're starting with the products. I wrote carbon dioxide first, so that's the first product that I'm going to write down in my equation. So 3 for the coefficient. Going to open up some brackets here and put in my number for the heat of formation for carbon dioxide, negative 393.5. Again, units all along the way, kilojoules per mole. It's the sum of the enthalpy in the products. So now I go on to the water. I have 4 of them. And heat of formation for water, negative 241.8 kilojoules per mole. I like to put the square brackets around all of this. So all of this now, these are my products that I do have. And now I'm just going to minus the enthalpy in the reactants. And well, there really only is just one reactant because oxygen is 0, so I'm not even going to write it down. The only thing I need to write down is the propane. Again, it is negative, don't forget that, so minus negative 103.8 kilojoules per mole. So you plug those numbers into your calculator, and this is what you should end up with. So what does this number mean? Well, if you take 1 mole of propane and ignite it, then there is some energy that's released in the form of heat. How much is released? This much energy per mole. So what exactly is a mole of propane? Well, it turns out that it's 44.1 grams. So burning 44.1 grams of propane releases this much energy in the form of heat. That is what this calculation says. So let's go ahead and do one more. I'll just bump it up a little bit. So in this case, rather than starting with calculating the amount of energy in a mole, I'm giving you a realistic number for gasoline, which is made up primarily of the fuel octane that you might put into your car, and well, units that we use when we fill up a tank, and that is liters. So calculate the heat of combustion. So when you burn 1 liter of octane, how much energy is released in the form of heat. So a bunch of energy is going into moving the vehicle, but in fact even more of the input energy is going to be released in the form of heat. So let's go ahead and calculate what that actually is for 1 liter. So I do have some other information here, and that is the density of octane, and we'll see why that's kind of important, because initially we're going to calculate the energy per mole, and then we're going to figure out how much energy that is when we have 1 liter. So again, you need to start by writing and balancing the chemical reaction. So directly from the data booklet, octane is C8H18. This one is a liquid at room temperature, and we're burning it, of course, with oxygen, just a regular combustion reaction forming. Again, I'm going to write the carbon dioxide first, gas, and I'm going to write the water second, but it really doesn't matter. Gas as well for that one. I'll speed up the balancing a bit here. So I have 8 carbon on the left. I want to get 8 on the right. I've now balanced the carbon. I have 18 hydrogen on the left. I only have 2 on the right. If I stick a 9 in front though, 9 times 2 equals 18, and that balances the hydrogen. For the oxygen, how many do I have? 8 times 2. 8 times 2 contained within the carbon dioxide is 16, and 9 times 1 contained within the water is 9. So 16 plus 9 equals 25, which is an odd number. So for balancing combustion reactions, what we can do, if you have an odd number for the oxygen on the right-hand side, we actually get to write this coefficient as a fraction. It's not complicated. All you need to do is take whatever that odd number is and put it over 2. 25 over 2, and this is now balanced. And again, this is a 1 that we do have. This is per 1 mole of the octane. So what if you happen to get that wrong with balancing the oxygen? It's not going to matter because you don't use it in your calculation anyway. As long as you have these ones right, you will be fine. Okay, so our heat of combustion for this reaction. I'm not going to write down the equation. I'm not going to write down the given information. I'm just going to go directly into plugging the numbers in. I'm going to start with my carbon dioxide, and maybe I will just write that up above. So the CO2, first of all, is a negative 393.5 kilojoules per mole. How many do I have? I have 8. So I need to multiply that by 8. It's the sum of the enthalpy in the product. So now I move on to the water. So this is the water. It's negative 241.8 kilojoules per mole. How many do we have? We have 9. I'm going to multiply that by 9. Square brackets around all that, because all of these are my products. Not going to worry about the oxygen. I'm just going to minus the one reactant that we do have. And that's our octane. Directly from the data booklet, you can find it in there, and it's negative. Again, really important that you do have that negative in here. It is minus negative 250.1 kilojoules per mole. Plug the numbers into your calculator, and this is what you should come up with. Negative 5,074 0.1 kilojoules per mole. For every one of these, that's how much energy is released. But that's not what we have. We have 1 liter. So how much energy is released in a liter? Well, we need to figure out how many moles there are in 1 liter. So you might recall this equation here from previous science courses for mole calculations. Number of moles is equal to mass divided by molar mass. So what mass do we have? Well, we have 1 liter, and that's why I told you here about the density. In 1 liter, it's 703 grams. So to calculate how many moles of octane do we have? That's why we're using this equation. So the mass is 703 grams. But what about the molar mass? Again, this is from previous science courses like Science 10. But to calculate the molar mass, you need to go to the periodic table and you need to take a look at the atomic mass for the elements that make up that compound. Well, what's the compound? It's propane. So what do we have? We have carbon and we have hydrogen. So if you take a look at the periodic table, it will tell you the atomic mass for carbon is equal to 12.01 grams for every mole that you have. And for hydrogen, it's 1.01 grams per every mole that you have. So in our octane, we do have 1 mole, only we don't have 1 carbon, but we have 8. So we're going to take this number and we're going to multiply it by 8. And we have 18 hydrogen. We're going to take this number and we're going to multiply it by 18. So when you do that, 12.01 times 8 plus 1.01 times 18, what that gives you is now the molar mass for our octane. And that works out to 114.26 grams per mole. And again, this is molar mass for octane. Molar mass, or big M, for octane. So what does that allow us to do? Well, it allows us to calculate in 703 grams, or 1 liter, how many moles we actually have. How many moles of octane are there in 1 liter? So let's just go ahead and plug the numbers into this equation here then. So that's 703 grams. 703 grams divided by 114.26 grams per mole. Grams cancel out. We're left with moles. This is how many moles we have in 1 liter of gasoline, and it's 6.15. So we've calculated the amount of energy in 1 mole. That's the number right here. And now we know how many moles we have. So we're just going to take the number of moles that we have in 1 liter and times it by the energy per mole. Moles cancel out. We're left with kilojoules. And that number does work out to negative 31,219 kilojoules in 1 liter of octane.